Okay, science time. Today we're talking about field forces and electromagnetism. So this is the discussion for both lessons 3 and 4. You have done you've mostly done the work for lesson 3. And then after this discussion, you'll also do the work for lesson 4, but we're going to do these discussions at the same time. And so the title is Field Forces in General and Electromagnetism. The objective is diagram scale, proportion, and quantity in field forces. There's no way this is actually going to work. Look at how successfully this is erasing. All it's doing is like making some weird black powder over here, so that ain't good. I'm going to have to spray it. Yeah, you was right. Who said that? Me. Good job. Avery. Yeah. In partnership with our parents and community. Okay, what I just read it and now I've forgotten because I had a conversation. What was the objective? Diagram, I believe. Diagram scale, proportion, and quantity. I'm so happy to have that brown writing off of here because that didn't really match. Diagram scale, proportion, and quantity in field forces. You already know what I'm going to say next. Science time. No, I've already said that one. Tiana knows. What is the next thing I'm going to say, Tiana? Yeah, let's define it. So let's define what do I mean by field? What do we mean when we talk about field forces? Well, one way we can arrive upon the definition is to look at our bell work. The bell work reads, number 1 was diagram Earth's gravitational field, and number 2 was diagram the magnetic field of a magnet. So let's start with just this word. What is a field in any definition? What's a field? Okay, something covered in grass. So we have one definition of a field where we could say she needs wide open spaces. Right, that's a field. What else is a field? Area. And we use this both literally, like a length by width of a certain, wide open space. But we also use it metaphorically to mean like the field of automotive mechanics or the field of the study of electricity or the field of astronomy, you know what I mean? Like the field of psychology. So we can also mean, in quotes, area of study, etc. So it can be an area of thought, a field. What do all these things have in common? They're describing what? Space. Yeah, good. Space. And since we live in a universe that has 3 spatial dimensions, that any space that a thing occupies is going to be 3-dimensional. I wrote 3D. 3D is short for, in case you didn't know, 3-dimensional. So when we talk about a field in science, we're talking about a 3-dimensional space. And we're talking about force fields. We're talking about, well, why don't you tell me? That's my question. God bless you. You tell me. When we're talking about the force field or a field force? Very convenient. Shh, be quiet. Okay, so we are still talking about field forces. I would say that when we're talking about field forces, we're dealing with forces that do what? What verb should this sentence have? Forces that do what in a field? Forces that do what in a field? Okay, I'm just gonna say act, but yeah, attract is one version of that. Attract, or they could also sometimes attract or repel, but they act in a field, in a three-dimensional space, okay? And not necessarily in contact. Remember, we talked quite a lot earlier in the year about contact versus non-contact forces. But both of the examples we had from our bell work, gravity and electromagnetism, I believe that, okay, we almost had another fire drill. Both gravity and electromagnetism are non-contact forces, meaning that they don't have to be touching other objects in order to act. Whereas, remind me, what are some contact forces? What are some forces that do have to touch? Friction as an example, just the general like push force when something's pushing something else. So these two, though, gravity and electromagnetism, are not necessarily in contact. They are non-contact forces. That doesn't mean they can only work when they're not in contact, but they can work when they're not in contact. So tell me, how does gravity work? We've talked about this before, but here I've drawn a circle. What might this circle represent? It could represent Earth. It could represent the moon. It could represent some other planet or star. It could represent an apple. All of those things have mass and therefore exert gravity. But what's true of gravity? How will the force be acting? If this is an object, how will the force interact with other objects, even ones that it's not necessarily touching? They will all be attracted to it. So in gravitation, the force is only attractive, and all masses are attracted to all other masses. Remember, the equation was F sub g, the force of gravity, equals capital G times m1 times m2 over d squared. And you remember that this tells us, you don't have to have this equation memorized, but this tells us that the force of gravity depends on the mass of any two objects and the distance between them. It depends on the mass. The bigger the mass, the bigger the gravity. The sun exerts a stronger gravitational field than Earth does. Earth exerts a stronger gravitational field than an apple does, right? So the bigger the masses are, the stronger the gravity. And the further apart they are, the weaker the gravity. Yeah, the further apart they get, the weaker the gravity is. But realize that this also, even though I've drawn it in 2 dimensions, because that's how whiteboards work, it's actually acting in 3 dimensions, right? If I had a globe, can you just, Gash, will you yank that globe off the ceiling real quick? This may ruin the whole ceiling. It may ruin the globe. I'm really excited to see what happens here, but I want that globe. Just give her a yank off. Good, thank you. So here we have the slightly deflated, yeah. While it's down, maybe we'll blow her up again. But here we have a slightly deflated Earth. And if I have another massive object, which I'll use a eraser, in my diagram, which is 2-dimensional, it looks like, oh, it can come in from over here, or over here, or over here, right? But in reality, it can be anywhere in 3-dimensional space all the way around it, because it's a 3-dimensional field. So imagine this same diagram, but with arrows pointing at it from all different directions in 3 dimensions. That's gravity. Gravity is only attractive. Gravity only attracts objects. There's no such thing, as far as we know, as repulsive gravity. That was a good serve. Meanwhile, though, electromagnetism, as you saw in your lab, by the way, this is the force of what we would in our daily life call electricity and magnetism as one. They are actually one force, and we'll talk about the relationship between those in a second when we talk about, guess what, electromagnetism. But that force is a field force also. If we have, let's use the classic example of a bar magnet with north and south poles, which we've already talked about magnets in general. But if we have just some, not a permanent magnet, but some magnetic material, some ferromagnetic material, like iron filings, it's really good that this is all happening during, I'm just trying to make a video. All I'm trying to do in this one day is just make a video. If we put iron filings, I really hope that sound keeps happening. If we put iron filings all the way around it, we would see, and this is what I was hoping your lab would show, but again, I've drawn it in 2 dimensions, but if we had this in real life, we would see the iron filings pile up around it in 3 dimensions. They make kind of spiky structures in 3 dimensions. And that is expressed to us in the equation F sub E. What do you suppose the E stands for? Yeah, the force of, oh, not just electricity, electromagnetism is equal to the electromagnetic constant K times the two charges, Q1 and Q2, over d squared. And we talked last time about, do you see the similarity between these two equations? The answer is yes. You should see the similarity between these. A force, a field force, is equal to some universal constant times the quantities on which that depends divided by the distance between them. Now, one primary difference, obviously they're different forces, but a primary difference is that these charges can also be negative, which means that the electromagnetic force can either be negative or positive, which means it can either be, in the case of a magnet, what? How would that change if the force is negative or positive? Yeah, attractive or repulsive. Magnets can repel as well as attract. Whereas gravity was only attractive, magnets can repel or attract. But still, the farther apart they get, whether they're attracting or repelling, the farther apart they get, the weaker it is. Your book uses the example, I love this example, of a stink field. You know stink field? Like if there's a really stinky thing going on, like a pig dissection or a group of sophomores, or even if it's not stinky, you can really smell, like if someone smells like toast. If there's a source of smell, it's kind of like a field. It's not a force field. It's not causing an actual force. But the closer you get to it, the stronger the smell is, right? Maybe instead of a human being, which is kind of offensive, maybe it's a little pile of dog ice cream. It's just an ice cream cone. Maybe it's a very strongly scented ice cream cone. Or it looks like a pine tree. But whatever it is, the closer you get to that object, the stronger you can smell it. Mm-hmm. Even if it's a good smell, like my Scentsy is cranberry scented. When I'm over by my desk, I can smell it more than when I'm at the door. And when I'm down the hall, I can't smell it at all because I'm farther away and there's stuff blocking it. Really a convenient time for that to happen. Also, we are going to run out of time because we still have 10 minutes? Okay. So those are field forces. The things that I would like most for you to know about field forces is that their scale decreases the further away we get from the source of that field in space, and that these are both three-dimensional forces. It's kind of hard to diagram that on a flat whiteboard, but they are both three-dimensional forces. Now, as we return to electromagnetism, the idea of electromagnetism in general, this is the relationship between electricity, which we learned about in the last lesson, and magnetism, which we learned about in the lesson before that. And together we call them electromagnetism. And the basic principle of it is this. I have here this little hand crank. What is this little guy? You know what this is named? Generator, yeah, exactly right, a generator. And I'm going to just attach to it real quick an LED. I have not tested any of this. I thought about testing it. I thought, it'll be more exciting if I test it while we're doing the video so that if it fails, it makes me look like a fool. Poor professor, he can't do anything right. That's what you all will think when this doesn't work. So here I have attached my little hand crank generator, and it doesn't work. Why is it not working though, Isaiah? Does this one not function? I know it is. They are directional. Maybe the light bulb is not working. You know what is a cool thing that is true of this is that this generator is also a motor. If we apply, instead of applying a load to it to be generated, so power is generated, we instead apply power to it, it will act as a motor instead. So let's try that out. Let me open this battery here on camera while that noise is happening. I hope that noise keeps going more and more and more. It's an impact driver, I'm sure. They do the lesson on impact drivers about once every 6 months, and it has to be while I'm taking a video, of course. Let's see if this works. Boop. Check it out. Oh, so you saw that it worked for a second. So yeah, this thing does function. If we apply a load to it, as I said, it is a generator, which generates electric current, and we'll talk about current in a second. And if we apply instead of power source to it, it's now a motor. So you could use this. I could attach a wheel to that. I could have a little unicycle that Avery's mom could ride. But this is a motor, right? It's powering this as a motor. Another thing that it will do, you saw this in your lab. I'll just use the battery for it. This is a power source. And this is what I'm getting at. So we have this electrical wire here, and you saw this in your lab too. But I have this electrical wire wrapped around a nail. What's it going to do if I power it? It's going to become a magnet. Yeah, it's going to be an electromagnet. So I can use it to hopefully, give me a second while I attach this a little bit better. But if I power this wire wrapped around a magnet, still, there we go. Come on, electromagnet. Come on, electromagnet. Oh, maybe you can kind of see it's picking them up. Except for that it keeps getting loose because my hand is not holding it correctly. There we go. Can you tell that that I'm moving it with the magnetism? It is working, it's just not working super hot. Can you tell? Can you see? Do you remember this from your lab? Because the way that this works and the way that electromagnet works is that you hopefully found this in your lab, electricity flowing generates a magnetic field. And moving magnets generate electric current. So these are kind of like two sides of one coin. I'm going to put an equal sign between them. They're not the same thing, but in the case of this generator, what I'm doing is I'm physically moving a magnet. Inside, you can't really, it's clear so that you can see what's happening, but within this gray thing in here, there's a magnet moving around inside some wires. And as I do that, it generates an electric current. So when I move this magnet, when I physically move the magnet with my hand, it generates an electric current. And that would power a light bulb that apparently, if you do a good job and aren't a fool, works. I'll try it again. And the other side of that coin is that anytime that there's electricity flowing, like in the case of that electromagnet, it'll generate a magnetic field. In fact, oh, it is working. Oh, it is working. Turn the light off. It's just very faint. Turn the light off, please. Turn the light off, please. You see it? Is it on there? A little. A little. A moving a moving magnet generates electrical flow, and a moving magnet generates electrical flow, and electricity flowing generates a magnetic field. If you are charging your phone, one of the reasons that wires are usually insulated, although this still happens even if they are insulated, is that if you're charging your phone and there's lots of knots in your charging cord, or if it's in a loop, there will be a magnetic field in there. And sometimes that can interfere with itself and it'll make your phone slow down charging. But also you could use it to, pick up like bobby pins or something. You could try that. Usually it works way better if it is wrapped around something that is ferromagnetic, like a nail. Like this little guy would still be electromagnet, but it's not very strong. This makes it a lot stronger to have this ferromagnetic material in there. And the way that you make electromagnetic stronger is either more loops. This is something hopefully you discovered in your lab. Either more loops Every new loop increases the strength of the electromagnet, or increasing the voltage. Those are the two ways to make an electromagnet stronger. So if I make there be more loops and use a 9-volt battery, hopefully this will actually work. I can pick some of these up as the last thing in the video. Nope, just not at all. Do you have questions about electromagnetism or field forces? None? You feel like you got this pretty good? You had a question, Justine. What was it? It'll be something like, what did you try to write? Yeah. Yeah. Okay, did you figure it out though? And on that bombshell, it's time to end.